welcome everyone. It's a great pleasure to introduce Yuansi Chen from Duke. He graduated from École Polytechnique and then got his PhD in statistics at from Berkeley in 2019. After that, he was a postdoc fellow at data science in Zurich, and then he went to Department of Statistics at Duke University. So Yuansi made great fundamental progress on Kannan-Lovasz-Simonovits conjecture and applications to Bourgain slicing problem, and he will speak about it today. Welcome.
Yeah, thank you, Dimitri, for the nice introduction, and thank you, Alina and Yusuf and other organizers for the kind invitation. Unlike Dr. Nierenberg, I don't work on PD stuff, and I'm kind of a beginner in geometric analysis, but it's still a great honor for me to speak in one of these lectures. Thank you for the invitation. So today, I'm going to talk about some recent progress on the Kannan-Lovasz-Simonovits conjecture and Bourgain slicing problems. So this will be part one of the lecture, and on Friday we'll talk about the second part. So in the first part of the lecture, I will restate the KLS conjecture. Like Boaz already did part of the job, and it's very good. I can go a little bit faster there, and then. As Boaz mentioned, there are actually many proof techniques centered around this topic. But for me, actually, I practically only know one kind of proof techniques. And so we'll try to understand this proof technique called localization, or it's also called Pathwise Analysis, which is, I think, some name I recently learned from Ron and Eldon. And we'll do this localization technique through examples from the KLS 95 paper, Eldon 2013 paper, and also Liam and Pala 2017 paper. Okay, let's state the conjecture. The conjecture is about the isoperimetric coefficient of log concave densities. So the isoperimetric coefficient for any density is the boundary measure, the ratio between the boundary measure and the minimum of the set measure and its complement. So in this case, the density is uniform distribution over a convex set. We cut the convex set partition the convex set into S and S complement, and look at the boundary measure and take the ratio. And then when you take the infimum of all the subsets, you get the isoperimetric coefficient. And so if your set has some kind of bottleneck, then the isoperimetric coefficient will be small. Well, if your set is like roundish, and the isoperimetric coefficient will be large. Okay. So the log concave density, that was also defined. So you take, basically, if you take the log of this formula and its concavity kind of definition. And there are many log concave densities like Gaussian exponential. And as long as it can be written as e to the minus f with f a convex function. And a large class of log concave density is uniform distribution over a convex set. So the definition, you can see that we don't use the log definition because we want to include this uniform distribution over convex sets. Okay, and then the Kannan-Lovasz-Simonovits conjecture stated in 95 is saying that you have some kind of universal lower bound for the isoperimetric coefficient of any log concave density. And here you have to do some kind of normalization. It's a constant divided by some normalization for this log concave density. The normalization is exactly the square root of the spectral norm of the covariance of the density. And like like was explained, the normalization is actually the normalization based on the those partitions using half spaces or hyperplanes. So because you can prove the upper bound of the same form is achieved by half spaces, and it will prove in KLS 95. And usually people also state a simpler version of KLS conjecture, where you only state the conjecture for isotropic plot concave densities, those densities with mean zero and the variance identity. And then the way you state it is this lower bounded by universal constancy. Okay. Any questions about the statement? Okay, so let's get into this this main proof technique. So the pathwise analysis, I don't know actually where this name first appeared, but I learned from some of talks from Ron and Eldon. It is a meta technique to study properties of high-dimensional object, and Ron and Eldon recently summarized this proof technique. And it has actually appeared in many of the previous papers. So roughly how it works is in 3 steps. The first step, you have to introduce a process. It might be a stochastic process, or it might just be an iterative kind of algorithm that actually transforms your high-dimensional object to something else. And then you look at the transformed version of the high-dimensional object, or look at the process along a single path, like along a single path of transformation, and see that whether you can like prove things easy for that object in that single path. And then the associate, you want to relate the properties of the high-dimensional object with the properties of the things on a single path. You might also do some kind of averaging when you have a stochastic process, but yeah, I know it's not very clear here, but I will try to go through some examples and give you more details about this technique. Okay, so 3 examples here: the convex localization, also called needle decomposition in KLS 95, and then we can actually have a stochastic localization version of needle decomposition. I'll explain it. And then in the last, we'll explain the example stochastic localization in Lee and Vampala, where they got the lower bound 1 over n to the 1/4 in the KLS conjecture in 2017. That was the state of art before our paper in 2020. So the first example is needle decomposition example in KLS. So sorry, this slide is a little bit dense, but it's actually explaining a simple idea of this localization lemma in KLS 95. It is trying to say that if you have 2 semi-continuous is like close to continuous, but it can have some kind of jumps. You have 2 functions that are semi-continuous that integrates that to be positive, then you can find a one-dimensional integral, or you can find a one-dimensional integral that both integrals are going to be positive. It's just this lemma is trying to say. And so it's like instead of starting some integral in a high dimension, you can do it starting this integral is in the 1 dimension. And this kind of idea, so because the 1 dimension integral is like a needle, it's called like needle decomposition. And this idea goes to Payne and Weinberger in the 60s. So when they try to prove some Bourgain inequality. Okay, so in the KLS 95 paper, they were trying to use this technique to prove this diameter isoperimetric inequality. The way it's stated is slightly different than we have seen for the in the KLS conjecture. Here you have a partition of the space. You have S1, S2, and S3. And then you want the volume of S3 to be larger than distance between S1, S2 divided by the diameter of the density, and then minimum S1, S2. And if you take the limit that the distance between S1, S2 goes to 0, then you will recover our definition of the isoperimetric coefficient. Okay, so this roughly gives 1 over square root of n KLS bond, like isoperimetric coefficient in the KLS bond. You take the limit S1, S2 close, and also think about that when you do the normalization, that the covariance of the density is identity. You apply Chebyshev inequality, you get the effective dimension that most of the mass are in the radius of order square root of n. So this diameter will be of order square root of n. So that's why you get roughly the 1 over square root of n KLS bond. So let's try to prove this diameter isoperimetric inequality using the localization lemma. Okay, so the proof goes by contradiction. So first you assume the converse. So you assume that there exists S1, S2, and S3, so that this inequality is not satisfied. So it's like instead of larger than, you have less. And then this will be our G and H. Basically, assuming the converse, you get two integrals that integrates to be positive. And then we can apply the localization lemma. So here the G and H will be just some kind of indicator functions on S1, S2, and S3, and the linear combination. And then the converse says that integral is G larger than 0, integral of H is larger than 0. And then you can find a needle, like a one-dimensional integral that integrates to be positive. And instead of considering things in a high-dimensional space, like S1, S2, S3, now you have a needle that actually partitioned the space in a one-dimensional space, one-dimensional case, like this called C1, C2, and C3. So let's see. So yeah, so sorry, I should probably draw it here. Yeah, this way you get Z1, Z2, and Z3. Naturally, basically all the mass of your high dimensional density now becomes you can define the density basically on the needle, and by looking at the partition of Z1, Z2, and Z3. Okay, and then you basically from this these two one-dimensional inequalities, you get a one-dimensional inequality combined like this. This looks very similar to the high-dimensional isoperimetric inequality, and effectively it is a one-dimensional isoperimetric inequality you try to prove. And observe that one-dimensional needle also gives you some log concave distribution, and one-dimensional log concave distribution, we know how to prove isoperimetric inequalities. And also observe that for one-dimensional isoperimetric inequality, the diameter cannot be larger than the diameter of the high-dimensional density. So we will get a diameter. If we will get a diameter-based isoperimetric inequality for one-dimensional density, and then we can conclude that the contradiction conclude the proof by contradiction. Okay. So this is how we use the localization lemma, because it's basically the high dimensional isoperimetric inequality is difficult to prove. And we use the localization lemma to basically say that it is sufficient to study the isoperimetric inequality in a one-dimensional space. And this localization lemma is just relating the high dimensional and one-dimensional thing. And let's see how to prove this localization lemma. So Boaz explained a little bit. I will give a little bit more details. So this localization lemma is basically cutting the densities, or like play through Ninja with the densities. This is also a term from Ron and Eldon. So you start with two integrals that integrates to be positive. So integral of g is larger than 0, integral h is larger than 0. The idea of each step is to find a smaller space integral, but they are both positive. So you want to reduce the volume, reduce the space a little bit until it becomes a needle. So each step you will try to find a bisecting half space of G. So that the volume on H and the capital H and capital H complement is 1/2 of the original volume. This is possible because for any density, I'm trying to draw a convex set here, and then for any point in the convex set, you can draw you can draw a hyperplane, and then you can, centered on this point, you can rotate this hyperplane along one of the axes. Does not have to be like a fixed axis, but along one of the axes, you can rotate, and then you can compute the volume on the H and H complement. You take the difference. The difference will go through some positive number and to some negative number. And because this rotating, this process is continuous, it will go through 0 at some point. So by rotating this hyperplane, at some point, you will find a bisecting half space for G. Okay. And for this half spaces, capital H and H complement, one of the following must be held for H, because the H integral overall, it integrates to positive. Okay. So now we have find a half space H where both integral GH is positive. So we start with G and H, they are both positive. Then we have a half space, they are both positive. And we can do it again and again. To reduce the space smaller and smaller, each time we get a half space, R to the N to the half space. Okay, we can do it many times. And it requires some work to show that actually this is a process that actually converge, and you will end up with infinitesimal needle, because if the effective kind of dimension of the space is still larger than 2, you can still do this trick. Find a point, hyperplane, and rotate. It's only when you only have a needle, you cannot do this, find a point and rotate and then get to positive integrals. Okay, so that's why it actually end up with an infinitesimal needle. In practice, you have to like pick those points with some kind of rational kind of numbers, so that you get a countable kind of steps until you converge. But these are like technical details. Okay, so the localization technique is a type of pathwise analysis, as we try to summarize. So it introduces a process, it iteratively transforms the high-dimensional density to its half space and then smaller space until it becomes a needle. So you are kind of transforming this high-dimensional density in some way, okay? And then the inspect is you kind of observe that the isoperimetric inequality in one dimension is easy to prove. It's not that easy, but we know how to prove those things. And then associate, you kind of can relate. Some things are invariant when you do this process. So for example, in this example, the signs of those volume on the set S3 minus some constant times volume S1 is going to be constant along that process. And also, you know that the diameter does not increase. So if you want to prove a diameter-based isoperimetric inequality, it's a good process to use, because in the end, your diameter will not increase, will always be smaller or equal to the original diameter. And at the end, you also get a diameter-based isoperimetric inequality, and then you can relate them with each other. Okay. Any questions about this, this summary of localization? Okay, so the localization lemma, it has pros and cons. So first of all, it easily proves the, we have seen it easily proves diameter isoperimetric inequality, because you start with something with diameter d, you end up with something with diameter less or equal than d, okay? And it also proves the isoperimetric coefficient for alpha strongly log concave densities, where the density is e to the minus f, with f is the Hessian of f is larger than alpha identity. So basically, you can kind of extract kind of a Gaussian part in the density, and the isoperimetric coefficient is lower bounded by alpha square root of alpha over 2. This is easy to prove for one-dimensional strongly log concave densities. And we can use this localization lemma to prove the same, because if you start with the alpha strongly log concave density, like in every direction is larger than alpha, then the one-dimensional needle that you end up with will also be alpha strongly log concave. And that's why you can relate back and try to say something about the high-dimensional isoperimetric inequality, okay? But there's a problem trying to apply this localization lemma to the KLS conjecture. We only get 1 over square root of n kind of bound. We don't, instead of constant for the KLS conjecture. This is because the KLS conjecture's normalization we make is not about this alpha strongly log concave diameter. The normalization we want is the variance of the high dimensional density. And the variance of high dimensional density is not like precisely related to the variance of the one-dimensional density. They might not be of the same order in terms of the dimension. So you get some idea that you have some density uniform distribution in high D, and your needle, you don't have much control of how this needle end up with, because at each iteration you find a point, you rotate, and you don't try to control this process. So your needle might end up being some like very short kind of needle like this, or it might be a like very long needle like this. For diameter isoperimetric inequality, it was fine because it's just about that diameter. But for the variance-based isoperimetric inequality, which is in the KLS conjecture, you don't get this correct. Okay. So let's get to the second example, the Aerodynamic stochastic localization of the needle decomposition. So Aerodynamic stochastic localization is can be seen a generalization of this kind of localization technique, where basically the question Aerodynamic was trying to ask from some of his slides back in 2013, that he was trying to say that, can we get better control of the cuts when we cut the densities, or when we play this through ninja? So when we do this localization, basically we rotate the hyperplane, but we don't know where the hyperplane end up with. So we want to have a way to control, to know that exactly at each step how the density becomes, and have analytical way to control it. So one simple idea he was trying to say, that he was trying to use, is that instead of cutting the space arbitrarily by rotating hyperplanes, you can try to cut the space with random cuts. You find the first direction, θ1, and then cut the density into half and becomes K1. And then find the second direction and then cut the density and becomes K2 like this. You can do iteratively. And there is something invariant. You can roughly prove that if you start with some subset of volume 1/2 here, for example, and the intersection, so here, for example, like S1, the intersection, the volume of at case step, it should also concentrate around 1/2. So that is the invariant is good, but you still don't have much control of how actually the final kind of density look like. So actually, it's still kind of, I think it's many things are unknown about this process, but then he actually abandoned this idea and tried the second attempt. His second attempt in controlling the cuts is saying that instead of truncating into half space, which is really rough transformation, we can try to multiply by a small random linear function. So what do I mean by multiply by a small random linear function? I'm trying to use the color here. So you start with some dense uniform distribution over K like this. And the black color means density increased and light color means density decreased. So you try to find the direction θ1 and you multiply this original density by 1 plus epsilon x transpose θ1. So here, the density on the right-hand side of this cut increased a little bit. The density on the left-hand side of the cut decreased a little bit. Okay, and then you can continue with the second cut, and then on this side, the density increased furthermore, and this side density decreases. So this is a way you kind of transform your original density, the uniform distribution, to something that is like different than your original uniform distribution. Okay, this is basically his idea to transform it. And what's some properties of this second attempt? So one negative is that unlike the previous process in the localization, you start with something with a fixed volume ratio is 1/2, but during this process, you might not always keep the volume. Depends on how exactly you do it, but in general, you don't. And the good thing is that now you have this epsilon, like it's like a smoother kind of transformation, and you can actually let the epsilon tend to 0 to get a continuous process of this transformation. And we may have more tools to deal with that. And then also another positive point that iteratively, it might make appear some Gaussian part in your density. What do we mean by making up a Gaussian part? Is that if you happen to be multiplied by two small linear functions in the opposite direction, 1, 0, 0 and minus 1, 0, it's like you are lucky. Those directions are random, but you're lucky you multiply by two opposite directions. And you can see that when you multiply by 1 plus epsilon x1 plus times 1 minus epsilon x1, you get 1 minus epsilon square x1 square, which is roughly exponential of minus epsilon square x1 square. So what is this? This is basically what I mean that the Gaussian, you are kind of multiply a Gaussian density to your original density when you do this process for many steps, and you're lucky have those opposite directions, okay? And the exact kind of process when he tried to make this localization, this second attempt into mathematical like formalisms, and you get this kind of transformation. So you start with a log concave density P, and then you iteratively multiply your density P with the Gaussian density with some covariance and some intercept we are going to specify. And then you divide by the normalization constant. Okay, so it's just like multiply your density by a Gaussian. And what this intercept and what this covariance is the quadratic part is specified by this stochastic differential equation. So CT here, capital CT here is a PSD matrix, a flexible choice. It's some called control matrix. This control matrix can be chosen as like identity or some other kind of matrix. Think about its identity for now. And then it means that the Gaussian part of this density just increase linearly here. And the intercept term is kind of interesting. You have a Brownian motion term, and then you have the drift term here. Okay. So why is this? This looks like not very intuitive, but actually if you try to derive what is the derivative of PT, you can see that it can be related to the Eldon's second attempt from this stochastic differential equation. Take the derivative of dpt and you get the x transpose mu t. So here, sorry, here is mu t is the mean of the density at time t, and this mu t x minus mu t transpose ct 1/2 dwt pt x. So you are basically multiplying pt by a little linear function. So if you discretize, this will be just a pt x equals to ptx plus the pt plus 1x. It's like equals to the linear function. This is a linear function that I multiply to pt. And this Brownian motion part is basically specifying the random direction where you are multiplying this random function. Okay. So this is basically, so this differential equation is making his second attempt idea very concrete. Okay, let's see a visualization. So I cannot do the simulation in high dimensional settings, but I will do it in a 2-dimensional setting where your initial distribution is uniform distribution over a convex set, and this on xy, and z is the density value. And then you apply this stochastic localization, basically it transforms your density. So let's try to look at this. You can see that actually density got transformed. And then it makes appear some kind of Gaussian part, because linearly, if I choose zt equals to identity, this Gaussian part increase linearly, and in the end, it will basically, it becomes in the end, it becomes a Gaussian kind of distribution in the end. And if you run it for longer, it actually becomes a kind of sharper and sharper kind of Gaussian. And if you use a different random seed, the location of the Gaussian will be different. But the rough idea is that you are kind of transforming your original density by making appear this Gaussian. And okay, and you can get control of this. You can get control of like this location of the density in average sense, but you don't have the control of the individual kind of location of those Gaussians. Okay, any questions here? Okay, so how do we use this fancy kind of transformation or Eldon's stochastic localization to prove isoperimetric inequality? The question is that we can transform the density, but how do we relate the isoperimetric coefficient of the transformed version to the original one? Right here is the kind of the main idea here is that you want to prove that the boundary measure is larger than something times the minimum of the volume PS and PS complement. Okay, and the intermediate you use is this basically transform distribution. The first step you observe that the boundary measure is the average of the boundary measure at time t. This you use the martingale properties. This PT is martingale, and then expectation equals to where it starts with. And then at time t, you can prove some kind of isoperimetric inequality for the transformed density. Hopefully it is easier to prove than the original density, the isoperimetric equation for the original density. And then you can try to relate, basically, you just need to relate this isoperimetric inequality, isoperimetric coefficient at time t, so that it can be related to the isoperimetric coefficient of the density you want to prove. And then you want to control this volume of the set PTS at time t, so that it can be related to PS. So, okay, so you kind of have a high dimensional geometric problem at the beginning. You want to prove that the boundary measure is larger than this two volume PS and PS complement. But trying to use this stochastic localization, you end up with an analytic problem. Basically, you have a stochastic differential equation, and you want to contour the quantities like the isoperimeter inequality at time t and this the volume of set S at time t. Okay, so this is the key idea that makes this geometric problem trackable using this localization, stochastic localization proof technique. Okay, let's see how can we see this needle decomposition in the Eldon stochastic localization framework. Okay, so in the needle decomposition, we want to make appear this PT to become a needle, right? So how do we choose some parameters in the stochastic localization so that the transformation ends up with some needle? Let's take a look at the derivative of the PTS. So we define GT as PTS, and then we take the derivative. So here, GT is just integral of S of PTX dx, right? So when you take the derivative of GT is this, hopefully you have taken notes. This is just a martingale, like it's just a linear random function that is multiplied. Sorry. Right, so you can see it as this way. You have some random, so you have some random direction dwt, and then sorry, this must be 1/2, but this does not matter. You have some kind of integral of like, this is like the mean of the density in the subset S. So VT, you define this vector VT, and it's just in this form. And the claim is that if you choose the CT to be the rank n-1 matrix, where the columns are always orthogonal to VT, then you get needle decomposition. And the idea is that if you choose CT to be like this is always orthogonal to VT, and then this part will be 0. So this GT will never change because its different derivative is 0. So means that the volume of PTS is always stay the same. Okay. And what is other special about this is that this is rank n-1 matrix. So you will add a Gaussian part to your density, but not in all directions. There's some direction that is left when you add the Gaussian part. And if you add more and more, it can only leave like one direction that is does not have Gaussian part. The other directions have Gaussian part that accumulates, and the variance will decrease. Okay, so let's try to say this precisely. So to prove this, claim 1 is that CT is orthogonal to VT, so you have this PTS. So PTS is a constant equals to P0S equals to PS. Okay, and then if you run the stochastic localization for T larger enough, PT becomes a needle because the covariance in all the other directions has to decrease as 1/T, because the Gaussian part keeps increasing in all the other directions. Okay, and so it will become a needle. And for the one-dimensional density that you end up with for T large enough, it still has diameter D. It's the same diameter as the original density. So you get an isoperimeter coefficient for the one-dimensional needle. So this is the same as the original localization lemma. And combining these 3 points, we have this, we have a stochastic localization lemma. We have a stochastic localization version of the needle decomposition. basically you run this stochastic differential with a special control rank n-1 control matrix, and you end up with a needle, and you prove, you relate it back. So to summarize, it is still a kind of pathwise analysis where the process will be a stochastic process, the L-dan stochastic localization with rank n-1 matrix. You run it to a T that is very large, and you kind of see that when you run it to T very large, it becomes a needle. So one-dimensional isoperimeter inequality is easy to prove, and you can associate things back. You have this PTS, it remains constant. So this PTS equals to PS. So you don't have to worry about the change in the PS. Then you only care about the change in the isoperimetric coefficient, but the isoperimetric coefficient will be similar because if you have a density that's diameter D in the beginning, you end up with a density that is diameter less or equal than D. Okay, so that is the stochastic localization of needle decomposition. The question is that we have choose this control matrix like this. The question is like, can we do better here using other variants of this stochastic localization? And the answer is yes. So in Li and Van Pala 2017 paper, they have a version of stochastic localization which improves the KLS bond that we got from needle decomposition. The theorem is like this. So if you run control matrix CT with its identity and run it up to time t equals to 1 over square root of n, a constant over square root of n, and then you can prove, they claim that you can prove isoperimetric inequality for any isotropic log concave density of order 1 constant over n to the 1/4. So this is a better lower bound. This is closer to constant than the original lower bound that we got from needle decomposition in KLS 95, which is only 1 over n to the 1/2. Okay. And when you choose this CT to be identity, this basically the Gaussian part, this e to the minus x transpose bt x that is multiplied to your px, this bt is increased linearly. It's t times ct equals t times identity. Sorry, this is integral. Anyway. It's t times identity. So you kind of have this Gaussian part increased linearly, and you know that if you run it for a very large time, like we've seen in simulation, this Gaussian part will crush the original density, and it becomes kind of just a single point. So you have to do some kind of early stopping until so that you still have some information about your original density. You don't crush all the information into one point. Okay. Okay, how do we use the L-dan stochastic localization here? It's a similar inequalities here. First, like we start with, we only need to consider subsets of measure 1/2. Like Boas explained, it's proved in early paper and also in Millman 2009 that for long concave densities to prove isoperimetric inequality, you only need to consider subsets of measure 1/2 because some kind of convexity of this isoperimetric profile, but we don't explain here. So we want to prove the boundary measure is larger than something times the minimum of PS and PS complement. And the way you do it, you go through the transformed densities. The first step, you observe this martingale property, the expectation of the boundary measure equals to the original boundary measure. And then at time t, the interesting thing is that when you try to use the control matrix CT equals to identity, you add a Gaussian linearly that is increasing. When you add a Gaussian, it becomes a strongly log concave density, meaning that e to the minus f with Hessian fs larger than t. Does not have to, like it, you cannot do it for uniform distribution as well, but we we just do it like for simple cases. Then when you have a strongly log concave density, we know that we can prove that using other techniques or using the needle decomposition, that it has an isoperimetric coefficient, which is of order square root of t. Okay, so that's applying the isoperimetric inequality for the transformed log concave density and to make appear this t1/2. Okay, then to relate back to the PS and PS complement, you just need to, so these are like, this is just 1/2 and 1/2, right? So you just need to make sure that the PTS is always close to 1/2. It's not going to 0 or going to 1. Okay. And what you end up with is that you need to control the probability of PTS between 1/4 and 3/4. And the interesting thing here is that since you add a Gaussian linearly, so the longer you run it, seems like you have a much better isoperimetric inequality for the transform version. So you should have a much better isoperimetric inequality for the original density. But there's kind of trade-off. If you run it this for too long, and then with high probability, this PTS might end up with close to 0 or close to 1. Okay, then it kind of ruins a little bit the overall isoperimetric inequality. Okay, so it remains control this quantity, and let's try to look at this quantity and take derivative. So this quantity is we define it as like GT, and I kind of explained that when you take the derivative of this quantity, it becomes like a linear function multiplied to this PT, but now it's only over S. So this thing is not 0. So this thing is not 0, right? Because now we have chosen CT equals to identity is no longer orthogonal to this direction. So it's not 0. So to look at like how large this kind of variation is for like a stochastic process, we have to look at this quadratic variation here. The quadratic variation, you can see that you have a linear part that is square. So you can see that this quadratic variation can be bounded by the spectral norm of the covariance of this density at time t. So everything boils down to control the spectral norm of the density of the covariance of the density of time t. Okay, and let's look at if we can upper bound this spectral norm of AT at time t by 1/t for some t, then this GT integral is controlled, so GT remains to be constant. And at time t, we added some Gaussian part. So the t 1/2 will be the isoperimetric coefficient that we end up with. Okay. So yeah, everything boils down to control the spectral norm of this AT. And the covariance matrix, we can take the derivative of it. Its derivative looks okay. You have some like martingale part and you have some drift part. It's even like negative drift part. But this martingale part will cause some trouble when we try to bound the spectral norm of this matrix. Direct control of this spectral norm is difficult, and usually people use some kind of potential function. You take this AT to the power Q and then take the trace, and then use this gamma T of 1/Q as a proxy for spectral norm of AT. Okay, so Lee and Van Pala basically, they tried many Q, but the thing that worked for them is like Q equals to 2. Okay, how does it work? So when you choose this Q equals to 2, you are thinking about you're dealing with the trace of AT squared, and then you take the derivative of this phi t, again, you have some martingale part, you have some negative drift part, and then you have some third moment third order moment kind of appear in the drift part. And this was the difficult part in their proof, and they have some smart kind of tricks to bound this third moment. So basically you want to relate this third moment to something related to this phi t, that so a function of the third moment and the function of the second moment, right? So they end up proving that this difficult term will be bounded by phi t to the 3/2, which it kind of looks reasonable, but in general, it's not easy to prove this type of inequality. So they end up with the drift term is like this, and the martingale part is, they also have a good way to bound it, but does not matter too much. The main dependency comes from the drift term. And now you can see that if you take t equals to, so this phi t, so phi 0 is the trace of A0 for isotropic log concave, A0 square. For isotropic log concave density, you start with the order n phi 0, right? So here you have order n to the 3/2. So to keep this phi t always to be order n, you can only run it time t to 1/√n. So basically you can control this phi t up to t 1/√n, and you can control this phi t to be always of order √n, or always of the order of the original density. And keeping this of the order original density, make sure that AT spectral norm, do I have a slide? Sorry, AT spectral norm is less than √n. The integral of AT spectral norm is less of order 0 to t is of order 1, right? Then you basically control the probability of PT that is around 1/2, and the time you can run is 1/√n. So now go back to that inequality we try to prove isoparametric using Aerodynamic stochastic localization. So t to the 1/2 appear here, and you run it to t equals to 1/√n. You get n to the -1/4 here. This part you control is of order 1 because you have control 0 to t. Spectral norm of AT is less than 1. Right, so combine these two controls of this thing together, you get an isoparametric inequality of constant over n to the 1/4. Okay, any questions about this this proof? Okay, so we can also see this Lee and Van Pala use of stochastic localization as a type of pathwise analysis. So you start with, your process will be an Aerodynamic stochastic localization with a control matrix identity, but this time you have to early stop, because if you run too long, then you crush all the density to be a single point. It's not very easy to analyze then. You observe that this time isoparametric inequality for strongly log concave density is easy. When you run CT equals to identity, you add the Gaussian part, it becomes a strongly log concave density. It's easy. So this part is different than the needle decomposition where you observe actually it's one-dimensional log concave. One-dimensional isoparametric inequality is easy to prove, but here is like strongly log concave density isoparametric inequality is easy to prove. And you need to associate back, you need to relate this PTS minimum of this PTS and PTS complement with the minimum of PS and PS complement. And this is a way to kind of associate the properties of the low dimensional isoparametric inequality to the high dimensional one. And this part was not trivial because of this specific CT choice. Okay, what's next? So this time we have explained like 3 examples of this pathwise analysis. It's possible like basically to extend this Lee and Van Pala's idea. A natural extension is just to consider a larger Q. So if Q is large, then this gamma T to the 1/Q is closer to the spectral norm of AT. right? So we might get a better control of this PTS, but the calculation becomes trickier, and that has basically stuck them. They have some calculation like this in their paper, but got stuck at some point. And in our 2020 paper, we basically follow their idea that choosing a large Q, but have a kind of refined analysis, and we can get isoperimetric inequality with isoperimetric coefficient that has dimension dependency that n to the constant log n over log n to the 1/2. So this exponent, this log n over log n tend to 0 when n tend to infinity. So for large n, this exponent will be better than the 1/4 exponent they got before. It's kind of almost constant lower bound in the KLS conjecture. So in lecture 2, I will talk about, I think lecture 2 is intended to be a general audience lecture. So we'll talk about the KLS conjecture relation to other conjectures. And then we complete the proof, basically still see this as one type of pathwise analysis, but we need some kind of technically, like we need some smarter, or like not smarter, but like more technical kind of tricks to make the technical part work. And we will also talk about the several applications of this improving the KLS constant in KLS conjecture, and some future directions apply this technique to other high dimensional phenomena, some outlook. Okay, thank you.
Well, thank you, Yuansi, for a great lecture. Are there any questions? Maybe let me ask the first question then. I'm not sure if we discussed it before. So suppose I think we did last lecture, we talked a little bit about isoperimetric constant, where you divide not into 2 sets, but into 3 sets, right? It's like higher Cheeger constants. So, and they're related to higher eigenvalues as well. Does it make sense to ask, what could be a KLS conjecture for, dividing into several sets? I have no idea.
Yeah, that's a very good question. I have no idea, actually. I actually haven't really thought about this question. I think Boaz probably is better position to answer this type of question, but yeah. That's interesting. Do you see any kind of applications where this isoperimetric for 3 sets appear?
Well, I think there is some relation to the Cheeger inequality is related to the first non-zero Laplace eigenvalue, and higher isoperimetric constants are related to higher eigenvalues. I don't remember the exact bounds, but I think some people have thought about it.
Yeah, that's right. Yeah.
Yeah. So in the discrete case, in the graph case, yeah, you might get like higher order cliques from this higher order eigenvalues. That could make sense that you are sampling from this higher order cliques. Maybe that can help, but I'm not sure. And I don't see quite like in a continuous case, what will that be actually?
Yeah, I don't know. And
it's an interesting question. I was thinking about it, but I don't have the answer right now. Yeah.
So would anyone else like to ask? Please unmute yourself if you want. I mean, in that case, let me ask another question. maybe it's a continuation of a question I asked last time. Kind of also a KLS, but maybe on manifolds, right, where you have curved spaces. So so in the flat case, we want to say that the isochromatic constant is up to a dimensionless constant attained by hyperplanes. Now, the question asked is kind of about the stability of this thing. So suppose curvature is not zero, but not very large, right? I don't know, less than epsilon or something. Can you say that, and curvature could be in the richest sense, in the Riemann, whatever, make whatever assumption you like. Can you say that things are attained, by almost hyperplanes? Again, something about mean curvature. I'm not sure about what. So this is a little bit like stability. So suppose you are almost flat, then things should be attained by almost hyperplanes. Ideally, it would be something quantitative. If curvature is less than epsilon, then something about the optimal hypersurface you could, yeah.
That's also a very good question. So what will be the kind of the variance kind of here? Basically, you constrain the variance, right? Instead of saying you have curvature, like constant curvature, you have no curvature, but you allow concave and you have some variance constraint. In the manifold case, what will be the kind of this kind of variance kind of constraints?
Look, concave, I guess you can still define, right? Yeah. If you you just connect by a geodesic and then just follow that thing. I don't know. I'm not sure, but this is maybe like perhaps if you want to understand what happens in the curved case, that stability could maybe like the first question 0 that you could ask. The easiest possible question. I don't know.
Yeah, I agree. Yeah, it looks like a easy question, but I don't know. Yeah, I don't know much about it actually. Yeah.
Just as a follow-up to Dima's first question, so this Higher-Chigger inequalities for eigenvalues, they have been studied for graphs by Lee, Haran, and Trevisan. So there was a very nice paper about that. And then in the manifold case, there was a paper by Laurent Miclot, which actually also uses probabilistic techniques, and later by Miclot and Hassanejad. So there is certainly interest, at least from the spectral standpoint, in this Higher-Chigger inequalities.
Yeah, thank you. Thank you for the reference. Yeah.
But I guess the question is maybe, suppose you separate into like 3 sets, maybe you need, a bounded number of hyperplanes or something to realize it. Not 1 hyperplane, but I don't know, 2 or
yeah. That's interesting. Yeah.
Or maybe it's like something completely different. So I don't know.
May I ask a question?
I think Han has a question.
Yes, please ask.
Thank you. Can you hear me?
Yes.
Okay, great. So thank you for your talk. I'm curious. So at one point you mentioned in one of your slides on convex localization that you don't have good control over the variance, right?
Yes.
But then when you transitioned to stochastic localization, I don't know if you mentioned that issue again. And I was interested in basically, how does the stochastic localization, does it give you good control over the variance?
That's a very good question. I think I didn't do exact calculation here. Yeah, you are right that actually a priori, you don't have to deal with this diameter isoperimetry inequality anymore. You can deal with the stochastic version of this needle decomposition because you can calculate the variance. Yeah, but the difficulty in calculating the variance of the density will be similar difficulty that we have in trying to prove the original the KLS conjecture using Liev and Pala or using our paper in 2020. Yeah, you can try that. Use the same type of difficulty arise because the variance of the density just have very difficult kind of stochastic differential equation. I have to say that we did this analysis, but I still don't quite understand the exact evolution of this stochastic differential equation. If you are very good at this stochastic differential equation and can have a better handle of this differential equation, I think, yeah, you might be able to improve this KLS constant just analyzing this stochastic differential equation and just using the stochastic localization version of the needle decomposition. That is the kind of one idea I tried, but I was not very successful. Yeah.
Okay, thank you very much.
Are there any other questions? I guess I want to make a remark that kind of probabilistic or stochastic techniques have recently appeared, and you know, in a couple of problems like universality and random matrices, and then in the KLS in your work. So it's sort of interesting that some probabilistic approaches lead to very good progress on several problems. So
yeah, that's yeah, interesting.
That's kind of cool. That's cool.
I don't know. I don't know much about random matrices, but I'll take a look. So this pathwise analysis, actually, I think Ronan Eldon was invited by ICM to write a review paper about this, summarizing all these stochastic kind of techniques as a proof technique for several like important problems, and I think it should come up soon. But yeah,
very nice.
I think yeah, it's a very kind of exciting kind of proof technique. Yeah.
Okay, so if there are no further questions, thanks once again, Yuansi, for a great talk. And thank you everyone for coming. The last talk will be on Friday, same time and same Zoom.